Welcome to Talk+Water, the podcast that takes a deep dive into the world of water with those making waves. This is Todd Bottler, your host for Talk+Water. I'm also principal of collaborative water resolution, which you can find at waterdisputes.org. In addition, I'm editor-in-chief of Texas+Water and the Texas Water Journal, which are both free publications. My guest today is Dr. Jill Williamson. Jill is the Water Subsystems Manager for the International Space Station. She is also the Water Management Co-Task Lead for the Mars Campaign Office. Jill has 10 years of unique experience in water recycling and management for microgravity applications as found on the International Space Station. Jill currently manages the International Space Station's water recovery system to ensure pristine quality water is available for astronauts for food, rehydration, and drinks, as well as for the space station's payloads and oxygen generation. Jill has a BS in chemistry from the University of Central Missouri and a Master's of Science and a doctorate in analytical chemistry from the University of Memphis, where she specialized in developing water quality analyzers for the International Space Station's water recovery system architecture. Jill, welcome to Talk+Water, and thank you for making time to talk with me.
Yes, thank you. It's a pleasure to be able to talk.
Well, this is a real thrill for me because I am an amateur astronomer and have been since I was, a teenager, or actually probably before that. And I'm just, fascinated with all things space. And so anytime, water and space cross, it's really interesting to me. So let's start out with kind of our preliminaries and tell us about your background and in particular, when you developed kind of a career focus on water.
Yeah, thank you. Well, where did it all begin? I guess it all started when I was majoring in chemistry. I didn't really know what I wanted to do with my life, but I knew chemistry would open up a lot of doors. So I just thought, let's just do chemistry. I loved it in high school, so I knew I'd thrive in college. But once I was going to graduate with my bachelor's, I didn't also know what I wanted to do with my life. But I had learned of the program at the University of Memphis. There was a particular water research lab, and it was intriguing to me. At the time, the graduate program had a NASA EPSCoR grant. So it's just one of these funded programs to get to do awesome research. And I had the opportunity and potential to really participate in that effort. And so this research group, they had expertise in developing analytical instrumentations for water quality. So this resonated with me because I'm more of a real world applications minded rather than the theoretical and computational based research. So, and I also loved watching the CSI shows where you get to see all the scientists using all those sophisticated analytical instrumentation. So it was up my alley. I love the idea. But also water is just is and always will be important for all of humanity. So why not? Did I really think that this could potentially be a long-lasting career working within this water world? But being fresh out of college, you didn't really know what you wanted to do when you grow up. But reflecting back, though, it was the best career move, really, to go to this graduate program, and it really was a springboard to where I am today.
Well, that's great. And in the interest of full disclosure, my in-laws live in the Memphis area, and many of my relatives on my wife's side are graduates from the University of Memphis. And so they all tell me very good things about it. So you, from the University of Memphis, went to NASA. Tell me about your career at NASA. Of course, this is kind of the thing that when I was getting out of college in the 80s, I was trying to figure out, how can I get a job at NASA? Which, as you can see, I did not figure out. So I'm curious about how that developed and, what you've been doing there.
Yeah, so my heart has always had this affinity for NASA. I grew up wanting to be an astronaut, just like all the young kids growing up. But as I did grow up, I learned that I get motion sick. So how about I keep my feet on the ground, but let's figure out how to kind of be in that space world. So always wanted to work for NASA in some aspect. And again, having that chemistry degree, I knew that opened up a lot of doors. Didn't quite know how to make it work, but I guess manifestation, right? You believe, you dream it, you believe it, you make it so. But really that pivot point was through my graduate school. The program had this NASA EPSCoR grant, kind of got our way into the door. But I ended up ultimately getting a NASA sponsored fellowship that paid my way through grad school. And part of that program, I got to do internships or on-site mentorships with NASA employees and the programs. And so throughout my tenure through grad school, I got to go to the NASA Center, specifically the one located in Huntsville, Alabama, the Marshall Space Flight Center. And I did that off and on for several years. And I got to see all the great and wonderful things that NASA was doing, particularly in this water management, water recovery, revitalization efforts, as seen on the International Space Station. So I got to see firsthand how they do it. It was so cool and really neat. So I really just kind of set the stage. Okay, I can really see myself being part of this story. But I had to graduate and go get my big girl job somewhere else. Nobody was hiring at the time around the year I had graduated, but I was able to kind of go around the country. I got to try jobs in academia and jobs in industry. So I'm very thankful to have those experiences, but I had always kept my eye out for any of those NASA opportunities, and it happened. Something had opened up within the chemistry labs here in Huntsville, Alabama, and I got to hop onto the teams, and I just kind of continued on to this career arc that has now taken me to be this water manager for the ECLIS, or the Environmental Control and Life Systems, particularly on the water recovery side for NASA. So kind of a long arc to get there, but I'm so thrilled on all those little tangents you get to go on along the ride.
Well, that's great. And I mentor students, and I try to tell them, you're going to maybe not get where you want to go in your career directly, but, you can get there eventually if you keep on, working at it. And
yeah, absolutely. Yeah, because I've even told, sometimes you have to go far away to come home,
Right.
To say, sometimes you have to go on an adventure somewhere else to then kind of find your home base of where you want to kind of start your next chapter.
So as you told us, you worked on water quality analyzers for the space station at the University of Memphis. And so since then, you've broadened your work to the entire water recovery architecture for the space station. So tell us what that is and give us an overview of how it works.
Sure. So let's start essentially at the end of the line. So on the space station, we generate clean, potable grade water for crew to eat, drink, also to be used for oxygen generation and for the payloads and science experiments. So this water is extremely clean, and in fact, cleaner than what you drink here terrestrially. So we have a really good high quality product for all applications. Now, this water comes from water collected from our humidity in the cabin atmosphere, because we're trying to maintain good, comfortable t-shirt weather environment for the crew. And so with that, we have to remove the humidity levels. So that is collected and sent on for water processing. But the other half of the water that we recycle comes from the crew urine. And so essentially your metabolic loads that humans impart into the system, half the water is coming from your sweat, your perspiration, your breathing, but it also comes from the urine. So as it coming from the urine perspective, yes, we do collect and recover the water from urine. And so we specially collect this urine and we process it into our urine processor assembly. Now, this technology is based on vapor compression distillation. It's a fancy way of saying a fancy still. So we're essentially boiling away the water and then we're condensing it. We just do it essentially in a one-step process, and it's specially designed to work in microgravity. Now, this urine processor generates two products. One is the distillate water, our clean water, and it also generates a urine brine, essentially all the things that remain in urine when you take the water out. And so we call this brine. Now, we would normally throw this brine away. We reach a certain water recovery. It's still fluid. It's got has a lot of water still in it, but we now have new technology, and we call it the brine processor assembly that we have actively been using on the space station for several years now. So now we can actively recover that last remaining bit of water that we normally would have thrown away, and we're returning it back into the loop. So that is a phenomenal story. We celebrated that over this past year and a half or so, to where we're really buying down this risk trade of water management, trying to get as much water back into loop as possible. So that brine processor is a great value added in the pursuit for exploration technologies to lead us into Mars. Now, that urine processor assembly also, as we said, generates this distillate. So that's kind of the clean water, but it's not clean enough to drink. And so we will send that water over to the water processor assembly for that final polishing. That humidity condensate, as we spoke earlier, also goes to that water processor assembly. Now, this system, it utilizes a series of specialized filters that remove solids and dissolved contaminants through means of filters, resins, catalytic oxidation processes that ultimately provide this clean, sterilized water. This water also then receives a dose of iodine as our choice of biocides. So like that of your city water, typically that's using kind of chlorine-based disinfections, but we chose to use iodine as kind of our disinfectant. So at the end of the day, our water recovery, overall, the efficiencies, thanks to the urine processor and the brine processor and the water processor, that we can achieve over 98% of recycling water back into the loop. So we are very thrilled on where we're at. And it takes these unique technologies to target specifically these applications of recovering water within this microgravity environment.
So tell us a little bit about that. I think that's the thing that people probably don't really understand, is that the microgravity environment is so different. It makes everything that you do a real challenge.
Yeah, the challenge is microgravity. When we think of it at the end of the day, fluids behave differently in microgravity, and we then have to go the extra mile to encourage that fluid to go where we want it to go. We don't have that gravity assist to do the work we often take advantage of. Like water wants to drip down. Well, we can't have that happen in microgravity. That water is going to float off, go this way, go that way. But another challenge we have is as it relates to bubbles, that gas-liquid interface, that bubbles here on Earth with gravity, they'll naturally separate and dissipate. But in microgravities, these bubbles, they have no reason to separate out. They'll float where they want. And in fact, they often merge and form even larger bubbles, which can impact systems. You can't push large slugs of gas through certain pipes and plumbing, can be challenging to equipment. So we have to go and add additional components, equipments to encourage that separation of gas from liquid. We also have to use a vacuum assist while we use the bathroom to pull that waste away from the human body. Again, things you take advantage of, you don't think about here on the ground, but when you're having to use the bathroom in microgravity, we have to use a vacuum assist to help pull pull that stuff away from the body up in gravity. So throughout our systems, our regenerative systems, we do have gas separators, and we strategically use rotary or centrifugal motion to induce gravity so that we can take control of fluid flow in microgravity.
So you said add components. And so I'm just curious, space stations, I can't remember how many decades old it is, but I'm just wondering, is the water architecture fundamentally different than when the space station was originally, put together in orbit, or is it pretty much the same? How is it? It seems like it probably would have advanced quite a bit over time because of all the experience that you got from the astronauts living in the station.
Yeah, it's definitely evolved, but the fundamentals have always been there. You have to have clean air and you have to have water management, aka the humidity controls, and the wastewater has to go somewhere. And so we've always had to have those core technologies in place. Now they have advanced and been upgraded to address some of these lessons learned that we've obviously have learned throughout the years. Space flight is hard and is challenging, and things don't always go as planned. So we've always have these iterations in these technologies across the board. And so the space station, it was kind of staged and it evolved from small to medium to large. And so as applications and expansion grew, then you need to bring in more of this regenerative technologies to, again, close the loop so that we don't have to resupply everything that we need all the time. But yeah, microgravity and flight hardware is challenging, and we've had to make some pretty good pivots to improve technology. But at the end of the day, we know where we need to improve to go above and beyond, so that when we go to Mars, or wherever else, we are excited to go to, that we utilize what we've learned on the space station to kind of springboard into that next generation.
So in terms of things that you've learned, I've read off and on for years that developing an effective toilet was pretty difficult to do in space. And so I'm just curious, I know that was a technical challenge, a major technical challenge. Is that technology evolved to the point where it's not an issue like it maybe used to be, or what's kind of the status of that?
Yeah, the thing you don't think is important until it breaks, then you realize how important it is. Toilet is one of them, but we've had on the space station, we've had a Russian designed toilet in operation for these 20 plus years of operations. And at the end of the day, it is an awesome technology. It does exactly what it needs to do for us to operate. But there's always areas of improvements. And of course, we want to be able to again, look to the future and exploration and have a U.S. designed toilet on board. And to get that runtime is kind of where we're currently seeing some challenges. Again, space flight is hard and challenging. We've, again, had our lessons learned and we try to address things. But the U.S. designed toilet is seeing some varying degrees of challenges. We are thankful that we are learning these challenges now on the space station before we have to learn it the hard way when we are actually heading to Mars. So yes, there are some challenges with some of the toilet designs over these past several years, but this is just expected, right? It's
right.
It's challenging. It's hard. We learn from it, and we will have a much better product at the end of the day. So no doubt we'll figure out, whatever these challenges are and all those other little gremlins that might show up. I mean, that's just our bread and butter. We learn from our mistakes and we make it bigger, better, stronger, so that we can get this toilet up and running, get this U.S. designed toilet operating, preferably before the ISS program retires here, look into that 2030 year. So we got some time, but that the sand is ever falling from that time clock. So
gotcha.
Yep.
Gotcha. So just out of curiosity, how many toilets are there on the space station? And you have them in every module, or are they kind of concentrated in a couple of modules, or how's that work?
Yeah, it's not like a 3-bed, 2-bath house on the space station, at least on the U.S. side. So it is an international program, our space station. So we do have our international partners, and they kind of have their areas where they do a lot of their hardware management. But at least for the U.S. side, we only have the one toilet in operation, and the Russians have their own technology. And in fact, they got 2 versions that they are operating and sustaining. But, because they're also trying to, upgrade their technologies, even more reliable, add more insights, all the fun things that you do to make your hardware better. But so technically there are 3 toilets on orbit. When you have the visiting vehicles come on board, sometimes they will have their own little baby toilet that they can access. But at least for the U.S. side, we technically just have the one toilet. But we are, again, trying to fix that and have a U.S. design toilet kind of in parallel to this Russian design toilet.
And I get, in terms of hygiene, I know you don't have a shower or bath or anything. I guess the astronauts have some kind of wipes or something they use to keep clean, or
yeah, it's basically no rinse shampoos or soaps, right? So they can do their hygiene that they need to do, but we aren't having and generating like soapy water. So everything is just kind of in a state where it's wet wipes, dry wipes, no rinse shampoos as needed. But yeah, we're not generating that gray water that you might often hear, that soapy water, laundry water. We don't have that architecture on the space station because, again, microgravity, the bubbles and liquid, they don't play well in microgravity. So it's just a challenge that it's a burden to have to manage that. But if we get to any partial gravity, like the lunar surface or the Mars, now you have gravity assist, you have the buoyancy. Now we can get back that soapy water processing.
Okay. Well, if I was somehow an astronaut before the end of my days, I don't have much hair. I just shave my head. It's like, okay, that's one thing I don't have to do. I have to worry about that. So, and before we, a lot of what you've told me is really sounding familiar because, of course, we now have reuse where we have, direct from wastewater to potable drinking water systems. And so, I don't know if you're familiar with this in the space culture, but in water culture, we have a joke that goes, okay, so the good news is in the future, we're going to be drinking our wastewater. The bad news is there's not enough of it. So, we're always, especially in Texas, where we're always like running out of water. So recycling the resources that are on the station, it's got to be critical, I imagine, because you've got to bring stuff up there if you can't recycle it, right? And that's really expensive, and you're trying to save resupply flights probably for other things. And so I'm just curious, does the space station generate any resources?
Oh, absolutely. Yeah, you hit on kind of a key topic where, the resupplies can get pretty costly. But if you can make something, that's even cooler. But yeah, so we do specifically on oxygen. And so we do have an oxygen generation system where we take the potable water that we had just recycled. And that water, right, consists of hydrogen and oxygen. And we essentially split that molecule apart via electrolysis. And we generate oxygen gas for crew to drink, or sorry, you're not drinking gas, but oxygen to breathe. And we also then generate hydrogen gas. So that oxygen generation system generates the 2 products, oxygen and hydrogen. Now, we currently take the hydrogen gas and we vent it overboard. It is essentially just a byproduct. But it too can be a critical resource, particularly in this effort of trying to close the loop of recycling. We can, when the technology is available, we can take that hydrogen and we can react it with carbon dioxide. So we have to take that carbon dioxide out of the cabin atmosphere, and we can react those two together, and magically there's a reaction that can occur within a catalyst that we can generate and make brand new water, like brand new, like it's new water to us in the system. So
Yeah.
So we love this technology. It's a Sabatier technology. It's used in other applications here terrestrially. I think submarines technology take this idea of kind of repurposing these resources. And so this idea of throwing the hydrogen overboard right now is just what's needed. But this current technology that can do this process of taking this CO2, it's a byproduct, we ain't doing nothing else with it, but we can react with hydrogen and make this water. But that technology is currently not active on the ISS. It's going through some strategic upgrades to address some lessons learned to make it more robust and more reliable. So we look forward to trying it again. But right now that the hydrogen is just being vented overboard.
So I guess the hydrogen, I thought, maybe it was being used for fuel cells or something, but I guess that's maybe a little too dangerous.
Yeah, because now you have to hang on to it, store it, pressurize it. It's a little scary when you're in an already small contained vehicle floating around the Earth. But we have other propulsion needs that we don't have to use hydrogen, at least at this moment of time. But of course, as we look to exploration, we want to utilize every resource, every byproduct to our advantage.
Gotcha. So here's some basics. How do astronauts drink water and eat food in the space station? Because I imagine the food's got to be hydrated, whatever it is, or some of it does. So,
sure, yeah, because most of the time the food is dehydrated because water is heavy, and so if you need to get it off of Earth's surface, it costs a lot per by the pound, by the kilogram. It's pretty expensive. So often the food is dehydrated and they're in labeled bags. And it has the little recipe to say, hey, for your mashed potatoes, try, go get, 150 mils of hot water, and then you can give it time to hydrate, mush it around, and then essentially just kind of eat it out of that bag. Of course, crew will dispense it out in the cabin atmosphere to play with their food. Wouldn't you? In microgravity, you get to see your mashed potatoes floating around and you can go catch it with your mouth. I mean, they have a lot of fun up there. But we don't have your standard water fountain, your sink to get your water, but we have a potable water dispenser. And that's where crew interfaces to get their water. They have drink bags that they'll connect up to this dispenser, and then they can request a specific amount of volume for their recipe, for their sweet tea, or their Kool-Aid, or lemonade, or just water. And they can request specific amounts of water, and they can ask for either hot water or ambient. We don't have a cold water tap for them, unfortunately, but we do provide them the water through this water dispenser. Occasionally, though, the crew will receive the fresh food, fruits, veggies, pizzas, sandwiches. They will get some, during specific resupply missions, they will have access to some of that fresh food. But as we look for exploration, we need to be better about maybe growing our own food. So we do have some kind of food growing technologies actively being tested, and they're successful, and they're all being tried out on the space station. So Crew gets to have to make their food with the hot water, but also they get to grow their own food on occasion. So it's pretty neat. But we have access to Earth. It's just right around the corner, and down the clouds. There's Earth. So we still have access to give them this ability for the fresh food. But it's a little bit of whatever they need. often it's that dehydrated bags of food, and they'll rehydrate and they'll just kind of squeeze it out of the bags as they need.
So I'm curious, did they ever let any of the folks who are in Huntsville or Houston, wherever, or Florida, try any of that food? I mean, dehydrated food, just see what it tastes like? I mean,
oh, yeah. There's plenty of opportunities to have that food bag arrive, or the drink bag, and we'll have them out for display, when we have teams wanting to have some tours and what have you. So you can actually look at them, touch them. But yeah, on occasion, we do have the opportunity to fill a food bag and kind of partake in enjoying what crew is enjoying on a daily basis.
So what do you say? Is that a perk or not a perk? I'm just wondering, at being an astronaut, how good it is.
Hey, I think they're just thrilled to be up there, and whatever they give you, I think they would love it. Gotcha.
No, I can see that for sure. So you mentioned that you recycled, I think you said 98% of your water or something like that. And so I'm just wondering, it seems like at some point you probably have to bring some more water up there. Is that kind of something that, most resupply missions might have a little, or do you have like a one where, this resupply mission, we're going to take a lot of water up? How often does that go on?
Yeah, historically, we do have to do some resupply. We had to do it more often before we really fine-tuned our water recovery efficiencies, as we're seeing these past couple of years. But on occasion, right, we aren't at 100%. We are losing water regardless of how great our technology is. And so we do perform some resupply missions, but it's not very often for this true need for resupply. But we do launch water to support other needs, other water balances. And so we might be sending some more water up here soon, but it's not necessarily because we're losing water. But it's just, again, we're all needing to make sure we have contingencies in place, and just nice to have the extra water when we can. But again, the water is very heavy, and we don't try to take up that space in these resupplies when other more important things are needed.
So I guess I'm kind of wondering, the water you take up there, I guess, since you don't really like to have chlorine in the water, you probably have to treat it. If you're getting out of a municipal system there in Huntsville, you take that out, and then it's maybe some of that more pure water as a feedstock, or do you go ahead and add your iodine then? How's that?
Yeah, so we have very specific water quality requirements that is relatively stringent, but specific for space missions. And so the water that we do send up meets that pretty stringent water quality. And it will have the iodine as its disinfection. But yeah, the water gets polished on the ground. So it's not just the city water, but what we do, further polish it, clean it, and then we'll add in the iodine, and then we'll launch it.
You mentioned earlier some of the specific technology that's been developed, like the brine processor assembly. I'm curious, what are some of the innovations with regard to water use and reuse at the space station that have potential for application back on Earth?
Yeah, the interesting part about what we have on the ISS for our water recovery systems is it is very uniquely designed for microgravity. To say it's maybe more complicated than you ever need for terrestrial applications. So we do have some innovative designs and technology, but most of those reside for a microgravity type of application. Now, what we could then find is we often work with the vendors of components and hardware or suppliers, and we usually can't just take the commercial off-the-shelf product and launch it. We need it to be more robust and more reliable and just just more rugged. And so we have to work with the vendors to say, hey, this thing broke after, I don't know, 100,000 cycles, when in any other application terrestrially, that was more than enough. But we have to go above and beyond for a safety, hazard controls, and just reliability. So we work closely with the vendors and these suppliers to really make a stellar product for them. And so these companies can then choose to say, hey, that is a really great product, and they can make that a standard product for their catalogs to be available. So although we may not have like the true technology that you see on space station, like some of those components and materials can then be accessible and available for the world to be used around that vacuum distillation, that vacuum compression distillation, that core technology is just kind of a fundamental application, but that is being used just kind of all around the world to take really dirty water to make it safer water to be able to get put onto fields for food production or just back into the rivers and streams. So there has been some kind of, what we are using on the space station is already seeing similar, core technology used elsewhere.
So when you said that a lot of that technology that goes to space station is more robust and reliable, makes me think about your work with the Moon to Mars program. I imagine that, you got to have something that's reliable and robust if it's starting on that trip to Mars and back. Tell us about your work in that program.
Yeah, absolutely. The important part for all of these exploration missions is going to come down to mass and reliability are going to be some of the key metrics for us to either we need to hone in on the baseline technologies, or we can explore other means, because I now have partial gravity. To say now I can utilize this gravity effect. So now I can take maybe a simplified version of what we see on the space station and just retool it to now I have gravity assist and I don't have to have all these extra specialized components. So we are actively working many parallel efforts to understand how best to achieve this water recovery system across the board. And so we are looking towards, again, this partial gravity technologies, how we have to stabilize the urine on the station. We didn't talk too much about it earlier, but we do have to make sure that urine doesn't break down into like ammonia and solids precipitating out and all the bugs that can grow. And so we have a way to do it on the space station, but we are looking to go for a more green approach that takes less mass to do that stabilization. So we're looking at different areas of how can we do it on these kind of partial gravity missions. One of the other perspectives is this early on for these missions, they are considered more short-term durations, like 30-day missions, rather than like a 5-year mission or a 20-year mission that we're seeing on the space station. So now we can then focus the technology to kind of operate in 30-day increments, which then also takes into account of dormancy risks. So we have other areas of research to look at this idea of dormancy and mitigating like the biofilm growth that can accumulate over time. How can we minimize that growth? How can we recover from the growth? And or design the technology that be more component level replacements and very low mass, kind of smaller cartridges, if you think of it that way. So we're exploring a lot of different avenues to set us up for success for these partial gravity environments, but also short-term durations and that consideration for dormancy. So we're doing a lot of great and wonderful investigations. And we're learning that we have a lot more to learn because we have even more questions that we have to go chase and go investigate. So we don't have the answers yet, but at the end of the day, if we had to make a decision, we know what works on the space station's been working for 20 years. And so we always have a way to always get us to where we need to go, but we can always do better. We can get mass down and we can get that reliability up.
So microgravity environments are, I guess, there's gravity on the moon, there's gravity on Mars, but the trip from the moon to Mars is that going to require the spacecraft to spin to generate some gravity, or are you going to go from a situation where you get partial gravity, and then you don't have the gravity, and then you get partial gravity again?
Yeah, wouldn't that be cool to do a space odyssey kind of station where it's rotating?
Yeah.
That would be awesome. I may not be in any of our lifetimes for that technology, but who knows, right? There's also technology being developed in such a quick fashion. But what we currently are envisioning is just the transits as you're going from Earth to that new location has to be in that microgravity environment. And so we will then lean on the current technologies and what we'll be learning here in the next, 6 years for this microgravity perspective. But then we would then have envisioning kind of that next tier of technology that would then find itself on the surface. So then you're bringing along your partial gravity technology that's intended to work on the surface rather than in those transit vehicles.
So what are some of the unique water issues you think will be encountered, during a crewed mission to Mars or by colonists on Mars eventually?
Yeah, I think the unique challenges, I think, across the board, and it's not just for the water perspective, but it's distance, that you have to make your systems that reliable, robust, and have component level maintenance in mind. So we don't have that 2-day ship kind of frequency to replace these components and parts. And so we have to be diligent about selecting this technology so that it can make the trip from Earth to Mars and support the mission. They're there to do science and collect data. So it has to work throughout and the return back home. So the distance kind of at that programmatic level, I think is going to be really a big challenge for us to be able to manage. Communication from the crew to Earth for those subject matter experts will be delayed. And so now this idea of can you come up with some like machine learning, automated responses and fault responses to be able to recover. And they don't have to rely on the SMEs on the ground to kind of investigate it. So we're working on these different initiatives to see how again, to set us up for success. But at least to me, it's that distance and not having access to your 2-day shipper to bring back your resupply.
So I imagine that, or it would seem like they're going to take, if they go to Mars anytime soon, they're going to take the water that they need for the trip. But eventually, there might be some way to try to harvest some of the water that's on Mars and use it for a colony. Have you been giving that kind of problem much thought?
Yeah, obviously, if there's access to a lot of water or ice to turn into water, that will be part of the loop. Right? We'll bring in our water, so we'll bring it with us that we'll have to recycle and recover over and over and over again. But in any of that new water, the challenges will be actually safely harvesting the water and then how to properly filter it and process it, because it's a whole new unique quality of water, and if they're going to have trace contaminants that maybe we're not familiar with. So we'll have to learn more about what really is in this water, but also how are they just harvesting the water is going to be kind of the first big challenge, and how to efficiently, cost effectively get that water to get back in the loop.
Yeah, I guess until you got some samples of it, you don't really know what you're going to have to do to it for sure. I guess you can always speculate, but speculation's definitely not enough. I guess if, people's lives are depending on it. So why is it important to recover and recycle and generate all those vital resources for these missions.
Yeah, and I think we've kind of been touching on it throughout this discussion, but really at the end of the day, mass is king when we're thinking about these crewed missions. If you're launching something off of Earth's surface and up into lower Earth orbits or above and beyond as you head to the moon or to Mars, it takes a lot of money to be able to get that mass up in orbit. So although for short missions, it actually makes sense to bring your own resources, bring your water, bring your oxygen, and bring those canisters to clean your atmosphere. But as you are having a longer sustained presence, your luggage, quote unquote, of what you can pack for your resources, your air and your water and waste management, it can only take so much. So we have to recycle, we have to recover and close that loop, because you really just can't bring all of it with you. It's a significant mass penalty to do that. So when we think of space station as kind of our example case, is we're there to learn how to live in space. If I have these resupply missions always sending water and food and gas, air, all the things that keep humans alive, then there's no more room for science. So the more we can recycle and more we can recover that water, the more science we get to launch and the more opportunities to learn how we can live long-term in space.
Well, I know that a key issue in space exploration and in just the utilization of space at all is bringing down that cost per pound to get something in orbit. And I'm sure it's probably cheaper than it was relatively back in the 60s, but it's not cheap, even though it might be less expensive than it once was. So, Jill, let's go to the last question here. How can our listeners find out more about your work with NASA?
Yeah, so NASA does have a great resource. We have our own website, and yes, there's a lot of great and wonderful pieces of information that NASA does. It's not just space station. We're doing all sorts of fun things. But at least in our little world of air revitalization and water recovery, is we actually have a yearly conference that we submit publications into. And it's the International Conference on Environmental Systems. And yearly we get together and we discuss all the technologies we are actively learning, developing, and just all the stories as it relates to the ISS operations. But we do have a repository, and it's publicly available, and it's actually administered. You can find it through the Texas Tech University Library, and you can search all of our conference papers. So if you just want to just search water recovery, water status, or anything, oxygen generation, anything that you want to kind of learn about for the ISS, if you can't find it on our NASA websites, then I encourage you to go look for this particular conference that we actively support every year. And you can learn all kinds of things if you really want to get down to the technical levels. But you can still have fun along the way, I promise you. So
they have that conference in some fun places?
Yep. We every year it's in a new location. In fact, this last conference, we were in Louisville, Kentucky, but we also go international. So our last international trip, we were up in Calgary, Canada. So it is an international conference of sorts, and so most of it's kind of here domestically, but we do travel. And so I think even next year we're heading out over to Prague. So you'll see us over across the pond for next year's conference.
Louisville, Calgary, Prague. Think it'll ever be held on the moon?
Oh, we better start planning, huh?
Jill, this has been fun. Thank you for being part of Talk+Water.
Yeah, thank you for the invite. We obviously love talking about this and to share our story. So thank you for allowing me to tell this story.
Well, it's been a pleasure. And as I've said, beginning, space is something I've always been fascinated with, and I've been looking for an opportunity to talk about space and water. And you give me that opportunity. So thank you.
Oh, you're welcome.
This has been Talk+Water. My guest today was Jill Williamson, the Water Subsystems Manager for the International Space Station and the Water Management Co-Task Lead for the Mars Campaign Office. I want to thank you, the listener, for spending your valuable time on this podcast. And I also want to thank Anna Huff at the Meadow Center for Water and the Environment at Texas State University for getting each episode of Talk+Water ready to go. Ready for liftoff. How about that? I'm ready for launch. If you enjoyed our discussion today, please consider a review to let us know that. And again, my name's Todd Bottler. Let's talk water again soon.